get started again. Only 10 minutes late. So, in case you don't know who I am, my name is Steve Bishop. I'm the Senior Software Architect for Gartner Technical Services. And I have a website called programmingmadeeasy.com where I have a lot of tutorials. I have over 300 videos up there on tutorials on C# and other things, ASP.NET, all that good stuff. I actually work for a company called Gartner Technical Services, and we do have a site, gartnertechnical.com. We do everything for IT. We do software development, we do website building, and we do technical support for things like, you need a new computer, you need someone to manage your network, Active Directory, domain controller, you need someone to hook up your internet, that sort of thing. We do it all. I have a blog, tech.tid-bits.blogspot.com, and I know I still screwed that up. tech-tid-bits.blogspot.com. There we go. And I got everything up there, including software development stuff and technical support stuff goes up there too. Much better? Video, let's see. Okay. So, I do consulting in both IT and software development. I've been doing it for over 15 years. On the IT side, I've worked for companies that are Fortune 500 companies. I've worked in small little mom and pop shops that have 2 computers and just need to know how to make a website. I've done it all. SQL Server DBA, so I do administration for SQL servers as well. I'm a full .NET stack developer, but typically with .NET, because it's such a wide array of things you can do with it, there's typically some sort of speciality, and my specialty is in ASP.NET MVC and Web API. So that is what I emphasize on, but I can do it all. I've even done some stuff in Xamarin and WPF and all that good stuff. So that's a little bit about me. Hand soap in the 1920s. You remember the 1920s? No. I don't remember either. So back in the 1920s, there was this, hand soap was actually powdered, okay? And it came in these dispensers like this, and you can actually still find there. I've walked into places where they still have these, especially in like government offices. You'll find that they still have these dispensers like this. But back in the 1920s, the ivory bar was starting to become a thing, okay, which is obviously what we all use now. Well, some of us has the pump stuff, but the ivory soap bars are really, really popular. And they were starting to intrude on the market share of the powdered hand soaps because obviously it's much easier you can buy it right off the shelf. You don't have to have a special dispenser for it. You can just, it's easy for upkeep. I mean, as soon as you're done with it, either it's gone or you just throw it in the trash. And these things were hard to clean out. They got rusty. You'd have to change them out all the time, and they were expensive. It was an expensive solution for hand soap. So this was a fantastic solution. And one of the companies that was selling powdered hand soap was a company called Ketal Products Company. And this company was owned by a 21-year-old named Cleo. Now, he had a problem, obviously, because he had only hand soap that he could sell. This powdered hand soap. He wasn't selling the ivory stuff. And all the other products that Ketal Products Company had been previously making all fell off. They were all done. So the only thing that they sold was this powdered hand soap. And so this 21-year-old asks his brother to come help him out and try to figure out a solution to making Ketal Products continue to work. So Cleo and his brother Noah get to work to try to find some way to keep their company afloat. And they get a meeting in 1933 with Kroger. You know Kroger? Okay. So in 1933, they get a meeting with Kroger, and Kroger sees an opportunity for a product that doesn't yet exist. They know that there's an opportunity, there's a market for something, but the product hasn't been created yet. And that problem was coal stoves. So coal stoves back in the 1920s and 30s was the primary way that people heated up their food and heated up their houses, okay? But there was a problem with coal stoves, and that was it left this sooty, ashy residue all over the walls and the ceilings. And you can see on the picture that there's no piping for this, right? There's no ventilation with where all this coal smoke goes. It goes right into the house and it causes this icky, sooty, ashy residue all over everything. It's terrible. So Kroger has this meeting with Cleo and Noah, And they're like, so, can you make a cleaner for walls? And Noah at first is like, well, we just make soap. So, and Cleo's like, sure, yeah, we can do it, right? We need to save this company, so yeah, we can do it. Well, it turns out Noah is the smarter of the two. So he goes about trying to come up with the mixture, okay? He's got to come up with some solution for this wall cleaner. And he starts digging around all the items that he's got in the house, and he's taking different things and mixing them together and seeing what works. And he finally happens across this mixture of flour, water, salt, boric acid, and mineral oil, okay? And he takes this mixture and he heats it up. And after about 6 minutes, 6 to 8 minutes, it turns into this goopy, like, it's a gloopy, sticky kind of mixture, like a doughy kind of thing. And what you can do is you can take this dough and you can smack it up against the wall, rub it all over, and then just peel it right off. Worked great, right? It's a perfect solution. And so sure enough, they go to market and they call this stuff the Kotal wall cleaner, non-crumbly type. Great solution. It's off the charts. Everybody's buying this stuff up. They can't keep it on the shelf. So Kotal is back in fashion. They've got a great company and everything's going fantastic for them. But there is a lingering little problem on the horizon, and that is oil and gas. They're starting to become the main way that people heat their homes, because now you have oil furnaces, and gas is a much cleaner burning fuel for cooking around the house. And this doesn't leave the coal residue that the coal stoves do, so the coal stoves start to go out of market. And of course, with the coal stoves going out of market, there's no more coal smoke for the product, okay? So Noah, in 1949, he's got some problems. First, sales start to slow down, okay, obviously. That's what we were just talking about. The second thing is Cleo dies in a tragic airplane accident. So his brother dies. Makes him very sad. Okay, crap. So what is Noah gonna do? Well, Noah, who's still very unhappy, goes and talks to his nephew, Joe. And Joe, well, Noah's like, damn, you're handsome. That's a handsome looking guy there. Probably has like lots of girls that he's taken out at night and needs the money, right? So hey, come work for me. Right? So Joe's like, okay, sure, why not? I do need the money. And this, of course, makes Noah happy again, so all right. Okay, so now they've got this new partnership going between Noah, who's the brains of the operation, and Joe, who's basically the face of the operation. And it just so happens that Joe has a sister-in-law named Kay. Now, Kay works at a nursery. So Kay has all these kids that she's wrangling, and she's always got to come up with new ideas of what to do with the kids. And she thinks about it for a while, and she realizes her brother-in-law, he runs this company, Kotal, and they've got this product, this wall cleaner stuff that is goopy and messy and stuff, and the kids, every time she uses it around the house, the kids always dig into it and stuff. So she's going to bring it to the school with her one day, and she lets the kids play around with it. And the kids are just ecstatic. They love this stuff. So Kay goes to Joe and tells him all about how much the kids love this wall cleaner stuff. So what Joe decides to do next is pretty amazing, but that is not the topic of this conversation. This is about solid principles. Practices for making better code. Don't worry, there will be a payoff at the end. I will tell you exactly what happens with Joe.
I gotta guess.
Okay. So, solid principles practices for making better code. SOLID is actually an acronym. It stands for Single Responsibility Principle. And the Single Responsibility Principle states every module or class should have responsibility over a single, just one, part of the functionality provided by the software. Okay?
Okay.
The O stands for Open Closed Principle, and I'll give you a link to the slides so you can copy all this stuff down if you need to later.
Oh, cool.
Okay. Open-close principle, which stands for classes, or which says classes, modules, and functions should be open for extension but closed for modification. And that probably sounds very duplicitous, right? How can something be open for extension but closed for modification? Seems a little kind of duplicitous there, but we'll get to that. Liskov Substitution Principle. This is the one that, when people try to remember the solid principles, this is the one that everybody seems to have trouble remembering how it works. And I think it has a lot to do with the fact that it's the only one with the person's name in it that created it. All the others actually have some sort of description about what it is. But the Liskov Substitution Principle is pretty important, especially if you use base classes. And that is, subclasses should be interchangeable with their base classes. Pretty simple. You should be able to have a base class, and then any subclass that derives from that should be swappable. You should be able to put that subclass in wherever that base class is. Okay? Interface Segregation Principle. Have you used interfaces?
No.
No? Okay. Do you know what an interface is?
I got a short explanation before getting here. But
Okay, no problem. No problem. We'll go over it a little bit.
Yeah.
You're lucky that you're the only one here because I can actually go over that with you.
Awesome.
So no client should be forced to depend on methods it does not use. So no client, and this means like a class that uses an interface, no client should be forced to depend on methods it does not use. And essentially what that works out to is make smaller interfaces and more of them, okay? And then finally, the D in solid stands for Dependency Inversion Principle. Have you heard of Dependency Injection? No, okay, good, because Dependency Injection is one people often get confused with the Dependency Inversion Principle. They're not the same thing, but they are related. Okay, and we'll go over Dependency Injection also. So Dependency Inversion Principle basically says high-level modules should not depend on low-level modules. Both should depend on abstractions. Okay? Do you know what abstractions are? We'll get over that too. Trust me, that's why we have this, that's why we're doing this talk. So high-level modules should not depend on low-level modules. High-level modules would be like your user interface, your database. Well, actually, that's more low-level. But all your low-level classes and your high-level classes should not have to rely directly upon each other. They actually both depend on abstractions. We'll talk about abstractions. There's abstract classes and interfaces. Have you heard of abstract classes or interface? Well, we talked about interfaces.
Well, yeah.
Abstract classes are very similar to interfaces. They're kind of two of the same thing.
Okay.
So, now, why would we want to do solid? Why is it important to do solid code? Well, that's because the result that we get out of doing solid code, on the good side of doing solid code, is that you get what's called decoupled code. That is, things don't directly rely upon other things. You have kind of an independence. Everything is siloed. So if something needs to be changed, it's very easy to change out. Okay? Which means it's easier to maintain your code. It's easier to extend your code to make other things work with the things you've already got. It's easier to replace the parts of your code, and it's also easier to test.
So everything is independent, but also simultaneously interdependent.
Yes,
okay.
Because they're all relying on abstractions. They only know that there's some sort of abstract thing that they can rely upon. They just don't know the concrete instance of what's going to be coming to them. They only know that there's something there, and we'll see that. You'll see some examples of that. Now, the bad of this is you have to do more thinking. Okay, you actually have to think about what it is you're doing. You can't just go, well, I'm going to start doing this.
Yeah.
Okay, more code. Maybe. It can take more time. Maybe. And it can cost more money. Maybe. Okay? These three things are very dependent upon a particular factor here. And let's just go over real quick how non-solid code looks when you go through the life of the project, the lifetime of the project. Have you ever heard of Agile?
Yeah. Okay.
So you have iterations that you're doing these things in, right? You're doing one iteration of code, then you have another block of code, then you have another block of code, and you do these, you release your code in these iterative styles, right? So let's say your first iteration, the new code, this light blue kind of aquamarine color is all new code. The top darker blue is legacy code that you have to support, okay? So the amount of time that you have on your first iteration to do new code is 100% because it's your first iteration. You get nothing but new code that you have to create. Iteration 2, you have to start supporting some of that code that you previously did, because anytime you want to make a change with something new, sometimes it's going to affect some of the older stuff, right? So you have to go and kind of modify and fix that older legacy code, right? You with me so far?
Yes.
Okay. And as we get more and more iterations down the road, we find that in order for us to make this 10 or 20% of new code, we end up having to spend a bunch of our time making the old legacy code work with the new changes that we're putting in. Have you experienced that?
With non-solid code, yes. Yes.
Yeah.
I know this is very familiar.
Yeah, very, very familiar, I'm sure. So what ends up happening though if you have solid code, it starts to look like this. Your first iteration, of course, is going to be mostly new code. Your second iteration, only about 20% of it is actually supporting or changing or fixing old code, because everything you start to do is about new. Same thing with iteration 3, and iteration 4, and iteration 5. Because everything is easier to maintain, it's more manageable, it's easy to swap out things. When things break, you just make a new one and put it in place. Which means by definition, you're creating something new to replace the old stuff instead of fixing the old stuff. So you actually create new things. Now, imagine for a moment that you are the client and you're receiving new stuff every time. You're getting everything you want implemented for each iteration is getting implemented. What kind of value does that have to the client?
Infinite.
Yeah, it's great, right? So all this great stuff, right? All this good, wonderful things that we can do for our clients by doing solid code. But obviously we have to understand how to do solid code. So one analogy I like to talk about with solid code, because the bottom line is when you do solid code, you make lots and lots of little things. In a typical non-solid code system, you can imagine that you're using big giant building blocks like this. So each one of these blocks represents a piece of your code, right? And they all form and fit together. Can you figure out what this thing is that's been created by these big blocks?
T-Rex.
You think that's a T-Rex?
Yeah.
Okay, what about, so we know that's a dinosaur. This is a dinosaur.
Yeah.
What about this thing?
Chicken.
A chicken? Yeah, maybe. I mean, we don't really know. We have no idea what that is, right? It could be a man, could be a chicken, could be, I don't know what it is. I don't really know. Okay, but if we use small blocks, not only can we tell that's a T-Rex, but I mean, look at the detail on this. Look at the detail on the tail. Look at the detail on the feet. You can tell it has bird-like feet. I mean, here, if we look at the big blocks, there's no bird-like feet there, right? We can't really tell the shape or the design of it. The tail is much better. I mean, the stability of this thing is better, right? We've got a tail that kind of equals out the weight of this thing so it can stand on 2 feet like that. It's not even relying on the tail anymore. You've even got teeth, which is really cool. They've got claws. You got so much more detail because you're using smaller building blocks to build this thing. Okay, so that's clearly a dinosaur. We know that that's a Tyrannosaurus Rex, and that's a man. We tell that's a man because we can see the detail on it, right?
Not a chicken.
Not a chicken. So let's go over each one of these solid principles one at a time. Single responsibility principle. What happens is when you use single responsibility principle in the way that it should be used, it actually creates the architecture of your application for you. Okay, so you don't have to think about architecture ahead of time. It just comes out of doing the single responsibility principle. And again, just to reiterate, the single responsibility principle states that every module or class should have responsibility over a single part of the functionality. Okay?
Yeah.
So one thing. That class or module should have responsibility of one thing, and that's it. Now, I find it ironic, I find it really funny that if you go and make an ASP.NET MVC core application out of the box, right out of the box, the first template that gets built by Microsoft when you go to create a new MVC application, the first thing that they give you is this thing called a home controller. You know what a controller is in MVC? Have you done MVC before?
No, I haven't done MVC before.
Okay. MVC is a way of making your code, it is decoupled code because you have models, you have views, and you have controllers. Your models are your data, your data objects. Okay, they define what is a person, what is a customer, what is a client, what is a phone number, what is an address. So you have these little things, classes that just specifically are like the properties that entail what each one of those things are, and we call those entities or models. Okay. So that's the M part. The V part is obviously the view. You create a view. MVC is a web architecture. So you create a view for your customers or your clients that come view the page. Your view is a separate entity that's just going to have the HTML markup language and also Razor markup language, which is how we integrate code into a view. So if you want to pull data from a model and put it into the view, you use Razor code. So that's basically what the view is. And then a controller is basically what choreographs this dance between the data over here, putting it into the view, and then returning it back to the user so they can view it on their browser.
So it's the thing that holds everything together.
Right. It's the choreographer, right?
Yeah.
When somebody calls the controller, okay, they call basically one of these actions: index, about, contact, or error. Okay, on the home controller, and the MVC architecture knows, based upon the URL that the user typed in or clicked on a link to get there, to call one of these different methods on that controller. Okay. Now what's interesting is, if you look at this home controller, this is what comes right out of the box. This is a class with 4 different methods on it. What does the contact action, what does the contact page have to do with the home page?
It's connected.
How?
Through a link.
Through links. But are they related in any way?
No.
No. There's just a link.
Yeah.
But there should be other controllers that the home page might link to too. Why are these 4 things grouped together in this home controller? What does an error page have to do with the home controller? Or the home page? What does the about page have to do with the home page? They're really all separate things.
Yeah.
But right out of the box, Microsoft is already putting us in this situation where we've got 4 different responsibilities that this one controller is in charge of. So they've already started us out down the path that's wrong. Right out of the box. That's the template you get and how they tell you how to do it. So what we really should do with this is we should isolate the home controller to just doing the index action.
Okay.
Okay? And then we take these other 3 actions and we create their own controllers. So that this about controller class has 1 action on it. This contact controller class has 1 action. Error controller has 1 action. So now we've isolated, we've split up each one of these controllers to handle 1 responsibility, 1 page that controller is in charge of pulling up. Does that make sense?
Yes.
Now, what I like to do is I like to create another class underneath this I call it the orchestrator class. I've seen it called the interactor. It's just basically where all my logic goes. So rather than have my about controller have all of the code behind the about action do anything, I actually make that logic in a whole other class altogether. And I just make that action, that about action, call the method on that operator. Okay? Same thing with my contact controller. It calls this method called getContactPage. And then my error controller actually the orchestrator has 2 different things that it does, because really, if I have an error in my application, I don't just want to show an error page, I also want to log the error. I want to keep track of where my errors are, right? So this orchestrator's got 2 different things that it does, sort of. Okay, we'll get to that a little bit later, but the error controller is asking the orchestrator to do whatever logic it is that I want it to do, rather than having the logic behind the controller itself. Okay?
And this is where interfaces come in?
We'll get to interfaces a little bit, yeah. So, then we have to have obviously the view that bring back to the customer or back to the user. We have to have something to show them when we're done, some sort of output, right? So our views, what the get about page view, about page action is going to do is it's going to return that about view. Same thing with this orchestrator, the contact view is going to be returned when the get contact page gets called. Same thing with the get error page. After it does the get error page and it logs the error, then it's going to return the error view. Okay? So we have our views. Now we have our models or entities where with different types of data. For my about page, for example, I might have a description stored in a database somewhere, right? Same thing with the email, phone number, and address. Those might change over time, so I keep them stored in a database, right? I don't want to hard code them in the code. I want to put them in some sort of storage facility somewhere that I can change it. Same with my error info, right? Whenever I'm logging my errors, I might want to save it to a text file or a database or something, okay? So those are my models, but the orchestrator is not going to talk directly to the data, right? Instead, we're going to have another thing in here. I call it a repository or a service, okay? So a repository is a special kind of pattern that allows you to easily swap out your sources. So if I have a description, let's say I have a database that's in Microsoft SQL Server, but we're going to switch over to a PostgreSQL Server, a different kind of database backend. Well, rather than have to have this orchestrator know everything about how to connect to that database, I have a repository instead that gives me how to connect to that database. And now I can swap easily. Every time this orchestrator needs to change databases, I just change the repository that it asks for, right? It makes it simple to just swap these out. Same thing for each one of these. Each one of these orchestrators has a repository, or perhaps it's a service, right? Maybe we're getting our service online from some sort of web API or WSC service or something like that, okay? But they also, notice that all these arrows, where are they pointing?
All to the methods there.
To my orchestrator.
Yeah.
Okay. These are my dependencies. Okay, my dependencies, what these classes rely upon are the yellow arrows. And it may look a little odd at first to see, well, the repository doesn't depend on the orchestrator, but the orchestrator doesn't depend on the repository. It doesn't care which repository it is. All it cares about is that there's some sort of repository that it's going to have. These are the directions we want the inheritance to go, or not the inheritance, but the dependencies to go. We don't want it to go the other way, okay? The question is, how do we do this, right? Which we'll get into.
Okay.
This is your domain layer. This is where all your business rules are. And really, these orchestrators are really just kind of like the top level entry into your business rules. They orchestrate the business rules. They orchestrate how the logic is supposed to go. And how do I get from this information? How do I take all this information from over here? Okay, now which view am I going to get and return back? So it's doing all of this stuff, and it doesn't have to do all the logic directly inside of it. Sometimes you want to break out that logic into their own classes and have the orchestrator call those classes functions instead. So sometimes we want to break it up like that. But this is really the entry to our domain layer or our application layer. Have you heard that term before? Domain layer, application layer?
I've heard it, yeah.
Okay. So this is just because we've split up the responsibilities, right? Mm-hmm. So by obeying the single responsibility principle, we've broken up each responsibility into their respective classes, okay? And what we end up with is our domain layer here. Here's our data access layer. You've probably heard that term before. Here's our service layer. You may have heard of that term before, or repository layer. Our user interface layer, and our API. That's our API layer.
Oh.
So just by following along with breaking up everything into these different responsibilities, we create these layers. We don't even have to think about this ahead of time. We don't even have to think about the architecture of our application as long as we obey, break everything up, okay? So that's pretty awesome, I think. I think that's a great way. Now the API, some people might be confused about this. I'm not confusing this with a web API. An API is basically the point, the end point of your application. Where does somebody get entry into and get data out of, right? That is what an API is. I need to call that function. That is my endpoint that I call, and I receive this data back. That is exactly what an API is. So these controllers are your API. They define what the endpoints of your application are that somebody can call and what kind of data is going to be returned. Okay, so we have separated out the call layer, the API layer, separate from the UI layer, and here's our data access layer and our service layer, but the domain layers where all the business rules are going to figure everything out, and they're all just kind of, they're all separate, right? We've got a real nice architecture here as a result. So the open-close principle. Classes, modules, and functions should be open for extension, but closed for modification. Let's start out with this little function here. Public void do something, where we instantiate an instance of new business rule and assign it to this variable called business rule. And then we execute. We call the execute method on that business rule, right? You've probably seen code like this.
Yes.
Right? Very simple. But there's a problem. This is very coupled code. There's a direct reliance. This do something method has a direct reliance on that business rule. If I make a change to business rule, what happens to my do something method?
It completely changes what that method
Exactly.
completes.
And now I have to go find everywhere in my code where this business rule is being created, and I have to go fix that other method to use that, the new instance of my class. Right?
Yes.
So there's a problem. This is coupled code. I am coupling my methods with these classes because I've instantiated it right here inside of my method.
I'm so guilty of that.
Uh-huh.
Thank you.
Okay. This is better. Public void do something. Business rule as a parameter. Now, call execute method on that business rule. If I took the I out of this, this would probably make immediate sense to you, right? Instead of having do something, call, instantiate new business rule, it just gets passed in an instance of business rule and then executes it, right? That would make sense, right? Mm-hmm. But there would, if I did that, there would still be a dependency upon business rule doing exactly what it's supposed to. This I in front of business rule indicates that what you're actually passing in is an interface, okay? Now an interface is, I will talk more about interfaces, but they are essentially a contract. You know how you can base a class on another class, right? You have inheritance. You can create these things called interfaces, which are defining the members of a class. If I created an iBusiness rule interface, I would say on it, I am defining on it, this interface that there will be an execute method on it, okay? You know what a method signature is?
No.
Okay. This here is the method signature. Public void do something.
Okay.
Takes no parameters.
Mm-hmm.
That is the method signature. Okay? It's a public, has a public access modifier. It returns void. That's the name of it. And then if I had any parameters, it would be inside of there too.
Yeah.
This is also a signature. These two are different, right?
Mm-hmm.
So we could do something called method overloading, right? We could have these two methods could both be on the same class,
Yeah.
right? Because the signatures are different,
Yes.
okay? When you define an interface, you only define the signatures. You don't define the logic behind them,
Okay.
okay? So I only say a business rule has an execute method, and it's publicly available, and it returns void. So essentially, if I wanted to make an I do something interface, I would say on it, okay, the I do something class has this method called do something that is public and returns void. So you just define on an interface what the methods are. That if this class was going to inherit from I business rule, it must have those that execute method on it. Does that make sense? Mm-hmm. Are you sure?
Yeah, something somewhere has to say how it works.
Yes. and I'm creating what's called a contract. I am saying, I don't know how this business rule, I don't know what it's gonna do when you call the execute method. All I'm guaranteeing you is that there is an execute method. And now I could create business rule that implements iBusiness rule, or I could create new business rule that implements iBusiness rule. I could create second business rule that implements iBusiness rule. And I can guarantee that each one of those classes, because they implement iBusiness rule, all of them have a definition for the execute method. Therefore, this do something method doesn't care which of those classes I pass into it, just so long as they implement the iBusiness rule. Does that make sense? Because we know that the iBusiness rule must have an execute method on it, so it doesn't care which one of those classes, which concrete class you implement and pass into it, just so long as this do something method knows it can call execute. That's it. That's all that matters. Now this is what we call decoupled code. Because now the do something method doesn't care what instance of business rule you run, just as long as that business rule class implements iBusiness rule. That's all that it cares about, okay? iBusiness rule interfaces are an abstraction because they just define those methods. They just define the signatures. They don't define the logic, okay? Now, I'm gonna kick it up a notch. Public void do something list of iBusiness rule. So this time, I'm not passing in a single business rule. I'm gonna pass in a list of business rules. And then for each one of them, I'm gonna call the execute method.
Okay.
If I passed in just one business rule to this in a list, would it work?
Yeah.
What if I passed in 1,000,000 business rules into it? Would it work?
If it didn't crash.
Okay, if it didn't crash, right? It'd probably hang and somebody would go, click, come on, do something. But the bottom line is it works, right?
Yeah.
This won't fail. It's been extended, okay? We can add as many business rules as we want. We can send as many business rules to this as we want, as many or as few, and it will still work. This is ultimate cosmic power, right? We have extended the bejesus out of this little something that was just calling and executing this. Now we can actually call execute on anything. Any business rule that we want to pass into it, we can execute it, okay?
Yeah.
So we've supercharged this just by having 2 extra lines of code. All right, so that's the open close principle. Thinking about how you can make your methods do more without having to do a whole bunch more coding to make it happen, right? Just adding a for each loop and making a list. Is that a lot to do? No. But by thinking about these things ahead of time, of how can I make this more extensible? How can I make this method more extensible? You create the opportunity to do better things with it.
How can I make ultimate cosmic power?
Yeah, exactly. Okay, next one. Liskov Substitution Principle. Subclasses should be interchangeable with their base class.
All right, this is going to be entirely new from my perspective, so.
Okay. Liskov Substitution Principle. If it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. You shouldn't need batteries. Okay, so let's start off with this bird class. Bird class that eats, poops, and flies. Okay. Now the bird class works perfectly fine to inherit from for the pigeon class, because the pigeon eats, poops, and flies. That's perfectly fine. But what happens when we try to inherit bird class for penguin class?
You got a penguin that can fly.
You got apparently a penguin that can fly, and that's not good. Because penguins don't fly. We shouldn't have to try to implement fly, and if there was some logic here behind the fly, which there should be, right, between just a regular class, there's some sort of logic behind fly that does something. And the penguin class is going to inherit from it? Apparently, right. Like, penguins suddenly can fly. That's not right. So that won't work. We cannot inherit from bird class for penguin class. What we should have done was made bird class just eat and poop. Okay, now the penguin class can actually inherit from bird class, and that works perfectly fine. And now we change the original bird class to flying bird class, and we add the fly method to it. So now the flying bird class can inherit from bird class. That works fine, right? Because flying bird class can be replaced wherever we have bird class. This is fine. We can put a flying bird class in anywhere that there is bird class, right? Mm-hmm. And now our pigeon class, if we inherit from flying bird class, now not only can pigeon bird class inherit from or go wherever flying bird class is. So if we have flying bird class somewhere in our code that's being called upon, we can replace it with pigeon class and it'll work just fine, right? Because these methods still all exist. These are the same methods. And even if there was a bird class out there, we could still put a pigeon class in there and it would work just fine, right? Because even though wherever this bird class exists, wherever that code is, it's never going to call this fly function.
Yeah.
But it will be calling the eat and the poop, and it doesn't really matter. It still works. The pigeon class can be replaced wherever bird class is. The pigeon class can be replaced wherever flying bird class is. And penguin class can go wherever bird class is, but it can't do this way.
Yeah.
Okay? That is the Liskov Substitution Principle. Okay? You should be able to, all your subclasses should be interchangeable with their base class. So I have a base class here. This subclass of the base class could go in wherever this is. And then same here. This pigeon class could go in anywhere this class is or this class is, which this inherits down the line from, right? So it can go in any one of those other two places. That is the Liskov Substitution Principle. Now we have the Interface Segregation Principle. No client should be forced to depend on methods it does not use. This is very similar to the Liskov Substitution Principle. The two often get conflated with one another, but there is a slight little distinction here. So let's start off again with our pigeon class and our penguin class. Okay, the pigeon class, we know we want it to eat, poop, and fly. Penguin class just eats and poops. All right. We're going to create iBird, an interface that just defines that any class that inherits from iBird must implement eat and poop. Okay, and again, an interface doesn't have any actual logic behind it. It just defines the members. There is an eat method on here, there is a poop method on here. So penguin class can inherit from this iBird interface, no problem. No problem at all. We could make pigeon class also inherit from iBird. We could, but there's actually something better we can do because we've got this fly method here, which is not defined by the interface. Okay, so this would work, but there's something better. Instead, let's create another interface that defines that, I'm going to call it an iFly interface, that says that any class that inherits from iFly must have a fly method on it. Okay? Now, what we can do is we can actually add a third interface, because interfaces can inherit from multiple classes, right? That was something we couldn't do back here with the Liskov Substitution Principle, right? You can only inherit from one base class, okay, right? Interfaces work differently, and that's why we like them so much, is because I can create an interface called iFlyingBird that inherits from both iBird and iFly.
Okay.
Now I could say my pigeon class inherits from iFlyingBird. And in fact, I didn't even really need this. I could have said my pigeon class inherits both from iFly and iBird. That would have worked just fine too. But I like doing this. I like to be able to do this wherever possible. Create some sort of combination. This interface, I guarantee, combines both of those two things. And now I can create a pigeon class, I can create a sparrow class, I can create a dove class, I can create whatever kind of classes, and just keep inheriting from that iFlyingBird. And I'm guaranteeing that those classes that inherit from iFlyingBird will have the iFly method, the eat, and the poop method. Okay, so now my pigeon class inherits from iFlyingBird, has all three of those, and here's the kicker. Anywhere, any three of these classes are so back when I did my interface and that do something method, I was saying it needed some iBusiness rule. I could pass in an iBird, I could pass in an iFly, or I could pass in an iFlying bird, and the pigeon class could be the concrete instance that would implement in any of those cases. So if my do something method just needed to make sure that you call the fly method on it, I could pass in a pigeon class.
Okay.
Right? But the penguin class, since it's inheriting from iBird, it doesn't inherit from iFly, you can't pass in the penguin class. That make sense?
Okay.
Question? You look quizzical.
I think it might be easier to, I get it very conceptually, it might be easier to see it sort of.
In code.
Yeah.
I got code for you a little bit later.
Thank you.
Yeah, no problem. I just kind of want to cover these conceptually first, and then we'll go into some code.
Yeah.
Okay, so that's the interface segregation principle. Now this is the thing that makes it separate from the Liskov substitution principle. We're saying that iFlying bird, we cannot force the penguin class to inherit from iFlying bird because of the iFly method. We cannot force the penguin class to inherit from iFly or iFlying bird because that would force it to implement iFly. But the penguin class doesn't have any way to fly. So what we would end up probably doing is throwing like some not implemented exception. Like this method exists, but I haven't done anything with it. Or just returns void. That's kind of lazy. You don't really want to do that.
Yeah.
Okay, or returns the default of something. You don't want to do that. You don't want to just return the default of what it expects if it shouldn't even implement it. Okay. Now finally, Dependency Inversion Principle. High-level modules should not depend on low-level modules. Both should depend on abstractions. So interfaces primarily, but you could also do something called abstract classes. So, we have that orchestrator class. And what we're saying here is that anything that goes into it and anything that comes out of it should be an abstraction, not a concrete instance. Okay? It receives information through interfaces, does something on those things, and then it sends back out through interfaces. The only exception to that would be if you're using a primitive, like a string or an int or a double. If your function is returning a basic string, int, double, decimal, something like that, and a non-complex object back, then that's perfectly fine. But if you are going to have a class that orchestrator is supposed to return back, it should be sending back an abstraction, saying that what I'm going to send you back is an interface. Okay? Mm-hmm. Now what we do is we have this business rule over here that also has abstractions that its inputs and outputs are. So we don't have any concrete classes here that are defined in any of them. That's because we're saying, remember in the open-close principle, no new objects. We don't want to be instantiating a new object in either of these two things. Right? We don't want our orchestrators to be instantiating a new instance of anything because now we're coupling our code. Same thing with the business rule. We don't want to instantiate a new thing, even if that is what's supposed to go out. Right? Even if that object that's supposed to go back out of the business rule, if it's a complex object, we don't want to new up that complex object. We want to say, no, it's an abstraction that we're sending back to you. That way both of these two things don't depend directly upon each other like that. There's no coupled code here. So what we have is like two interfaces. One, let's say iRepository and iResponse. So your iRepository is your connection to your database, right? It's how your CRUD actions are being exposed. Create, read, update, delete, right? You've heard the CRUD acronym before, I imagine. So your iRepository exposes the create, read, update, delete of whatever that object is that you're going to create, update, or delete. iResponse, this is interesting. This is probably something you're never going to hear. I don't know, I'm not going to say I'm the one that created this idea. I don't think I am. It just came like out of thinking about this and doing this enough times. The response object that the orchestrator should expect back from the business rule should be an iResponse object, some sort of abstraction, right? So the orchestrator expects it's going to send it a repository, but it's also going to send it an iResponse, some sort of class that implements iResponse and send it to the business rule. So this is already defining what it expects back before the business rule even gets it. There's also something out there you may have heard of called an IOC container. Have you heard of that term before? Inversion of control container. I also call it a dependency resolver. IOC container has many different names, but essentially what it is this I repository, you can define in a IOC container that if there is an instance of I repository needed somewhere, then the DB repository is the class that should be sent to it instead, if that makes sense. So this is kind of like watching. It's monitoring to see what are the classes that these things need. Send over this concrete instance, okay? So when this orchestrator sends over, I forgot I had that little thing there, sends over the I repository and the I response, what's actually happening is the dependency resolver picks up on this transaction and actually sends a business rule in a DB repository in place. So as far as the orchestrator is concerned, it doesn't know that this is happening. It's just handing off an I repository and an I response. These are two abstract concepts. An I repository and an I response. It doesn't know what that entails. All it knows is that it has one, it's going to pass it along to the business rule. Now the business rule is going to do whatever it's going to do and then hand back the I response back to the orchestrator. Okay? But in the background, this dependency resolver is actually, okay, you need an I response? Well, I'm going to create a business rule response. Okay?
Okay.
Again, you'll see this in code, I promise.
So,
and go ahead.
The dependency resolver is sort of like a middleman that is always there in case either the business rule or the orchestrator has a change to it so that they don't have to directly depend on each other.
Right, yeah, because all the orchestrator and the business rule care about is that I have one of these interfaces. Okay, I'm being sent a class that implements I repository. I'm being sent a class of that implements I response. And here's some code here that this whole construct sounds a little complicated being explained, but when you see it like this in code, it probably makes a lot more sense. I have my business rule method. It takes I repository. It takes it as a parameter, takes an I repository interface. So some class like DB repository can be passed into it and it'll be assigned to the repo object, right? The repo parameter. It also should take the response. So this orchestrator is going to expect some sort of response, but the orchestrator is actually passing in the response that it expects. Now all that's going to happen is the business rule itself is going to take and call the getAll method on the repository, because that's what we've defined on DB repository or any I repository class. Any class that inherits from I repository has this getAll method on it. Okay? The business rule doesn't care what it does. All it knows is that it can call that getAll method. And that getAll method will return a response that we're going to assign to this variable called model. And now we're going to assign model to the response.model. Okay, so here's our repository and our response. All we're doing is we're taking the getAll, we're taking whatever comes from that and assigning it to the model property on that response that was handed to it. And then we're just returning the response back out because there's our I response. So the inputs, I repository and I response, are abstracts. What it sends back is an abstract.
Yeah, okay.
Make sense?
Yeah.
This is where the actual good stuff happens. But as far as the business rules cares, it doesn't need to know what the concrete instance is. It just needs to know that it can call getAll and that there's a model property on it. That's all it cares about. It's up to the orchestrator to figure out what are these two things that it should be sending it. Does that make sense?
Yes.
Okay. This part here is called dependency injection. Everything that this business rule method requires to do its job is being injected. So all the dependencies of this business rule are being injected into the parameters of method. Now typically, this actually happens in the constructor of a class. For illustrative purposes, I've done it in the method, but typically these, like the iRepository, would actually go into the constructor of the class, okay? I assume you know what constructors are.
No, I'm sort of just...
Okay.
Yeah.
So, that is what the difference is between the two. So let's do some workshop stuff. Build an application that takes a vehicle make and vehicle year from the user, and based on a set of business rules, accepts or rejects the entry. Okay, this is what we're going to work on. Build an application that takes a vehicle make and a vehicle year from the user, and based on a set of business rules, accepts or rejects the entry. The rules are as follows. The user could enter either a 2 or a 4-digit year. The make does not need to be case sensitive. We are only accepting Mazdas 1997 and newer, and we are only accepting Toyotas between 2006 and 1999. Okay, so those are the only business rules that we have. I have a GitHub repo of the solution for you. Okay, so if you go to github.com/xipoo at /solid principles demo, I have 2 versions of the answer here. One is a non-solid solution where everything is in one class. The second version, everything is broken down into solid, okay, into all the different components and parts that it's going to need. Joe McVicker made Play-Doh.
I knew it.
So there you go, Joe McVicker. He did not necessarily invent Play-Doh. His uncle did, Noah, but Joe McVicker capitalized on it, decided to remarket the wall cleaner as Play-Doh and put coloring to it. And now that's what we know it as, is Play-Doh. So.